Well, so my name is Antoine Llor, and I'm going to talk about recent work we've done at CEA, the Commissariat à l'énergie atomique, the Atomic Energy Commission, and about geometry, energy, and entropy compatible variational approaches to fluid dynamics, for computational fluid dynamics. So before starting, I want to make a short warning, because I mean, this is a very math-oriented conference, and what you're going to hear now is basically a talk on numerical schemes, on practical numerical schemes, so schemes that are supposed to be used in industry, as seen by a practitioner. I'm a practitioner, so no big, beautiful theories, and but application of basic geometrical principles, sometimes beyond strict mathematical rigor. And we'll spend a large first part as on background from other scientific communities, which I think are relevant with respect to our demands. And you see we have a lot of slides, but we'll skip many of them, which are redundant with what you've seen previously. And so my apologies. Whoops, what happened? My apologies, and please avoid throwing rotten tomatoes. So this is the outline. We'll start with our motivations, which basically boil down to a spec list for the hydrocodes that we use at CEA, and also in other industrial applications. And we'll go on the GEEC background and on about the general principles on making the least action principle for fluid dynamics. And then we'll exemplify this with two cases. One is, I would say, the simplest case, which is a Lagrangian fluid system, and the other is a complex multi-fluid Ale scheme. So, at CEA we have a large facility near Bordeaux with a megajoule laser. So you can see the hall with all the lasers, and they're focused and converge on an experimental experimental chamber. This doesn't work. Yes, it works. Here at the center of this chamber you have a small pellet, small target of a deuterium-tritium mixture, and when at the center of a hole realm, which acts as a sort of X-ray oven, where the laser radiation is transformed into X-rays, and the radiation pressure implodes the pellet and eventually reaches ignition. So if we want to simulate this kind of flows, we have a very stringent demands on our hydrocodes. Basically, the implosion of laser targets is a mixture of isentropic compression and expansion phases, weak and strong shocks, which generate entropy, and for which, of course, we need to have accurate conservation of mass, momentum, and energy in order to capture the Huguenot jump conditions across shocks. Transport over long distances with many fluids with ugly equations of state, because we start at cryogenic temperatures and end up in plasma states at hundreds of thousands of degrees, and undergoing mixing due to many hydrodynamic instabilities, and coupled to many other non-standard physical phenomena such as radiation. So this is a lot of issues to solve at the same time, and many of these features are actually found in numerous other academic and industrial situations. So our main, and these are related concerns, our main concern is robustness and entropy consistency, and then only accuracy, okay? Because if the code doesn't work, because basically it crashes, you're not thinking about accuracy in the first place, of course. So now, running an isentropic flow is like walking the edge of the cliff, because you have non-negligible numerical residues that can be of uncontrolled sign, and these eventually can crash codes. And remember, for Murphy's law, if anything can go wrong, it will, and it does. I mean, it's everyday issues that we have to face. So, other industrial contexts, pipe flows with slugs. This is of interest in many industries, especially the oil industry. So there's been a lot of developments in this area, and these codes, all these codes are 1D codes, okay? And they sell in hundreds of thousands of dollars per year and per processor, okay? And they have issues with entropy, of course. Here is an example. This is from the nuclear energy. Yes, the simulation of the loss of coolant accident. You may know that in the primary cooling circuit of a pressurized water reactor, you have water at 300 degrees Celsius and 150 atmospheres. And of course, one of the worst accidents that can happen is that sudden a loss of the sudden opening of the primary circuit, and this generates blowdown. So all the water suddenly vaporizes. You have expansion waves that start traveling all around and can destroy the rods, the nuclear reactor. And so this has been studied for a long time now, and some experiments in the early 70s, and for instance, did this on, you see you have a long pipe filled with this water at 300 degrees Celsius, and you have a sort of a guillotine that suddenly opens one end of the pipe, and you have sensors all around. One of the sensors, pressure sensor here, you see at the bottom of the pipe, has this was the measurement, and the early simulations back in the 70s actually, well, the code worked well there, and then the pressure went down all the way to 0, and then the code crashed, of course. And the guys there spent 2 years trying to work out what was going on. Entropy was, of course, somewhere in the blue. And here is another example. So this is a very, very simple test case that is used in all these pipe flows. It's called the ransom faucet test. It's basically completely isentropic. So you have an input of water at 10 meters per second in a chamber, and you have gravity. So you have a flow stream that stretches due to gravity, and you have air coming up to fill in the gap here. And so basically this profile can be simulated, and most of the codes that actually use a 4-equation model, so 2 mass conservations for water and air and 2 momentum equations for water and air, but algebraic closures for the internal energies of water and air. Well, all of these codes basically get nice results. You have, of course, numerical diffusion and other small artifacts, but they're well understood, and basically if you increase the number of mesh cells, you eventually recover proper convergence. Now, if you carry out the simulation this with a more extended model, with the 6-equation model, where you add this time evolution equations for the internal energy, so you integrate basically d equal minus pdv plus TDS that should be 0, but happens to be not exactly 0 because you're doing numerics. Well, some people manage to do well. Some others here start producing some really strange artifacts, or ask for enormous number of cells in the calculations in order to recover something sensible, of course. And believe me, these are not the worst results, because the worst results were published by people who have very powerful positions as editors in leading journals. Okay, so we can talk about that later. So the numeric options that we need for our applications for laser targets basically we have long distance transport and isentropic accuracy. This is pushing for Lagrangian schemes where we follow the material. In contrast, we have instabilities and vorticity, and this pushes for Eulerian schemes, which are much more stable, but they are over-diffusive. Lagrangian schemes are too fragile when you have vorticity because it distorts the mesh. So we can get the best of both worlds by using arbitrary Lagrange-Euler schemes where we have a sort of motion of the grid that captures part of the Lagrangian evolution, but not fully. So we add mixing. We are going to use multi-fluid models. So this gets a multi-AL scheme. And in a multi-AL scheme, you see that the hidden entropy production and from your numerical scheme is actually going to be a residue coming from the variation of energy because it's forced by energy conservation, and all the PDV contributions coming from velocity divergence, relative drift between the fluids, transport of fluid from one cell to another, cell volume changes because you're doing AL and so on. So you have to keep track of all this at once. So just to put some flesh here, here is the simulation of a classical test case, the Taylor-Sedef expansion. You have a strong energy, internal energy at the central cell here, and the rest of the fluid is a ideal gas at 0 temperature, and you have a shock expanding from the origin here. So this is the calculation on a Eulerian grid with 240 square grids. Here is the Lagrangian, which achieves about the same accuracy on the shock, same resolution on the shock, with much fewer grids, cells, 30 to the square. But if you look at here, you have the central cell, which has considerably expanded and distorted all the mesh here. So this calculation is still stable, but if you have a little bit of vorticity, it crashes quite easily. Here is what an AL calculation looks like. So you see that the central cell has somewhat expanded, but not too much. This is a strategy for the grid motion that is initially mostly Eulerian, and at late times it's mostly Lagrangian. Okay, so back to the origins of computer fluid dynamics. You have basically two schemes. You have the von Neumann-Richtmeier, which was developed during the war, published in 1950. And very first Titre scheme, it's Lagrangian. It was basically finite differences and in a leapfrog configuration, and using artificial viscosity to stabilize the shocks. But it has only approximate conservation of energy. It's up to the scheme's order. And when you have a shock, of course, you have a discontinuity where you can have a significant error on the energy. However, it's still in use in our niche applications because it has excellent isentropic behavior. Yet, of course, it is deprecated in academia because of this lack of conservation. The second scheme, a noticeable scheme that appeared, was Godunov's scheme back in published in 1959, but in his thesis already in 54, which is a completely different approach. It's finite volumes, fully centered variables. It has exact energy conservation and an intrinsic dissipation coming from a Riemann solver at faces. So you don't need to have the artificial viscosity of the von Neumann-Richtmeier scheme. And it was later simplified and extended to generate almost all of the present-day CFD schemes. And the multidimensional Lagrangian extensions are complex, unstable, and over-dissipative. Theoretically, it's very well grounded, and with important, there is an important theorem there, the Godunov's theorem. Okay, so from there, many people tried to fix this issue of the conservation in the von Neumann scheme and didn't really succeed. So eventually, until a few years ago, there was a spread unsupported belief of the impossibility of performing this. And in the 2000, Depré, Mazran, Mer et al. Came up with a Godunov scheme that worked well on Lagrangian's setting, but was over-dissipative. But in 2016, we published a paper where we eventually managed to get the full conservation of the leapfrog scheme. Now, this work here eventually provided us with the roadmap to apply to general hydro scheme, and we call this roadmap the GEEC, Geometry, Energy, and Entropy Compatibility. So how does it work? Well, you know the least action principle. You know that Newton's law is equivalent to the Euler-Lagrange equations, which are equivalent to the least action integral. Least action principle. And so we have seen this for many talks now. So it has here the basic properties. A few examples from mechanics. This is very classical. Just one point here I want to stress. If we have a two-fluid system, for instance, with air bubbles moving in water, air bubbles have inertia in water, which is not given by the mass of air in the bubbles, but by the added mass, so the water that is actually displaced when the bubbles move. And so this means that in the Lagrangian, you need to add an extra kinetic energy term here, which involves the velocity difference between the two phases that you're considering. And this, of course, makes the momentum not equal to the usual velocity times partial density. It means velocity plus this velocity difference. Okay, for mechanics of simple point masses, this is absolutely useless. For complex systems, the least action principle is really useful. And okay, this I can skip. Now, the founding statement for our GEEC approach is this: isentropic flow is geometric. And in isentropic flow, the internal energy only depends on density, which in turn only depends on the system configuration, which is defined by the diffeomorphism. So how do you go from the initial configuration xi to the actual configuration x at time t? Okay, so or by the fluid element trajectory is this equivalent. So basically the internal energy is now not dependent on entropy, or depending on the entropy, which is a Lagrangian invariant. So therefore, in this setting, the least action principle applies, including in the discretized systems. Okay, so we generate numerical schemes through mimetism of the action integral. This is actually a principle that was stated by Tonti back in 2014, and we've seen many presentations hinging on this principle. So here is the mimetic discretization. We have the continuous action integral. Well, we decide to discretize it in time and space. We have a wide freedom of quadrature formulas that we can apply at this stage. And for instance, the second order, here is the action integral for a system of coupled point masses through some two-body forces. And here is the action integral that you would get for a discretized fluid with on cells C and with velocity at nodes P here. So the first one is the Verlet scheme, which is very widely used for molecular dynamics. The second one here turns out to be the action integral for the von Neumann-Richtmeier scheme. Okay, so the mimetic properties, of course, we have exact conservation, explicit. We have a symplectic form. Two theorems here are really important: is that we have only approximate conservation of total energy to the scheme order, and as was shown by Marsden and his student, we can only get 2 out of 3 properties. So in case we recover conservation of total energy, we will have only approximate symplecticity of the scheme. Okay, so the GEEC approach is first do the geometry. So the non-dissipative, part of the system, which is going to be isentropic, is derived from minimizing the discretized action integral. Then we correct this scheme, which is symplectic, into an energy conserving scheme, which is approximately symplectic. And then we add the entropy producing terms, the dissipation terms, added and defined generally by dissipation potentials. Okay, so the critical step here is the definition of the action integral. Everything else follows almost on a quasi-univocal way. Sorry. So the usual scheme designed on the Riemann solvers take the opposite tack. They start with an intrinsically dissipative method, and then they try to reduce dissipation in order to capture isentropic flow. Now, in this approach, there is no control volumes in the traditional sense. Energy balance is ensured on equations taken as finite differences from which duality operators, here U divergence of gradient P and P divergence U, are just a byproduct. And this, as I said, appeared when we revisited the VNR scheme. So, first example here is Lagrangian scheme for a single fluid. So the fluid is carried by Lagrangian cells C, labeled by C. No mass fluxes between the cells. Cells are polytopes defined at each time Tn by nodes labeled P. So the configuration geometry and the velocities are defined by node positions. The velocities are defined to second order at half integer time steps. The parenthesis is missing. Thus, the internal energy is defined at cells and integer time steps, but the kinetic energy is defined at nodes and half integer time steps. So we get this action integral with these definitions for the volumes. The volumes depend on the positions of the nodes, and the masses on the nodes are just the masses of the cells that have been redistributed in a conservative way. Now that the action integral is defined, everything else is a mere technicality. So, stationary action gives the momentum equation, where we have these corner vectors. The kinetic energy balance eventually provides the terms that need to appear in the energy equation. In the energy equation, we have corrective terms here that are not present in the original scheme. We add artificial viscous dissipation in order to capture this, shocks, and we enforce entropic production by forcing the artificial viscosity to fulfill this positivity condition. Okay, now we go to the multifluid system. So a multifluid system actually is an averaged system. So we start from the instantaneous equations for conservation of each of the fluids. Here C phi is the volume fraction of fluid phi. We have conservation of momentum and conservation of internal energy. And for stochastic systems at small scales, we do we can consider the average of these quantities. Generally, it's ensemble average, but we can use other averaging. So we have the average density, momentum, and internal energy. And when we plug this into the equations, we get this set of averaged equations on all the different average quantities: average velocity of fluid phi, average density of fluid phi, average volume fraction of fluid phi, all these quantities being defined at each point in time. And of course, we have correlations that appear in red here. And these are terms that need to be closed. For instance, Reynolds tensors, drag, viscosity, thermal dissipation, and so on. And when we don't know anything, what we can do is just do some modeling and say, okay, everything in red is 0. Okay, and we end up with what we call the backbone model, which happens to be exactly non-dissipative, so it is geometric. Okay, and also with the condition here that all the phases have the same pressure. So we can build a Lagrangian for this multiphase flow, and this Lagrangian here is written in Euler coordinates. So we have the kinetic energy of each of the fluids. Here the sum runs over all the different fluids, the internal energy of the fluids. Here we have the mass conservation of the fluids with a Lagrange multiplier here. So here we have the direct transport operator for the density. Because in Euler coordinates, we don't have any constraints between rho and u that we would have if we had Lagrangian coordinates. Lagrangian coordinates define the geometry, the connection between these two fields. And at the same time, here we have the link constraint that gives the conservation of Lagrangian coordinate psi. So we apply least action principle, and we end up with this equation. Now, we discretize this action integral, so you see it gets ugly, but it's there. I mean, there's no magic here. It's we have velocities, so it's an AL setting, so the nodes move with some velocity w, and the fluids move with respect to the mesh with velocity v, and here u is the sum of u and w recentered at the cell center. Here we have a transport operator, which is just first order upwinded. And when we do the least action principle on this, I will skip that, you eventually get that. Okay, looks ugly, but I mean, you just pull the string. It's fully explicit, and something funny happens here. The transport operator here is upwinded, okay, but the pressure gradient that appears in the momentum equation here is downwinded. And the downwinding here is different for each of the fluids. You can be upwind for one fluid, downwind for another fluid. So which way are you going to discretize the pressure gradient? Well, this variational principle tells you there's only one way to discretize the pressure gradient in order to be isentropic, and this is the way it is. So some related work, and here is the test. So what you see is 8 clouds of water moving in air at very high speed, 3,000 meters, and here is the mesh. So you see the calculation was done on a moving mesh. So this is an AL simulation, okay? The clouds initially are Gaussian, and they have a volume fraction, maximum volume fraction, which is about 15%. And as they move towards the center, they superimpose and they push away the air, and the residual volume fraction you have is only 4%, about less than 4%. So you see you get something really stable, really nice. Of course, we have numerical diffusion because we have first order transport. Okay, and I'm almost done. So concluding remarks. Ideas to bring home. Isentropic flow is especially important and fragile, even more so in multifluid systems, which are often physically complex and numerically ill-conditioned. However, it is possible to consistently generate multifluid dynamic schemes from hermetic variational quasi-symplectic approaches, even in complex settings. This is the GEEC approach that we've shown. Pressure forces and work couple all multifluid energy reservoirs and are thus potentially complicated and stiff, and they must be accurately calculated to avoid fatal energy entropy errors. These leads to unusual pressure gradient discretization schemes, and starting from an isentropic scheme profile, we have full versatility for adding physical or numerical dissipation processes. So these are the ongoing work. Extension with second-order monotonic transport, added mass dissipation terms, and gas particle flows that we're trying to work out with our students. And I thank my co-workers, some people who are very nice with some interesting ideas here, and most of all, my former student and now colleague, Thibaud Vazquez-Gonzalez. Thank you for your attention.